Hello, I'm Tom. I'm going to be speaking about assembly and software reverse engineering. So, who am I? What are my credentials? So WannaCry was a large ransomware attack in May 2017. It affected large organizations such as the NHS, FedEx, and other big important things, and also little important things and like many things. It affected a lot of things. We're going to be talking from the perspective of like WannaCry has just happened and we want to use reverse engineering to try to figure out how to stop it. So where do we begin? We start with assembly. Assembly consists of simple instructions such as moving a value from a register into memory or between registers and stuff like that. A register is just like a fixed-sized variable which is built into the CPU and so therefore can be accessed very quickly. However, due to the size of them, things that don't fit in registers have to go into memory. Memory takes longer to access, but it's still relatively quick. And it runs line by line like anything else does. So in memory, you have different segments which contain different parts of the code. And most memory segments aren't executable apart from the text segment, which holds the instructions that are being executed. The .data segment holds variables. Read-only data holds literals and constants that don't change within the program. The only exception is if a constant is defined but not given a value, in which case it's stored with the dynamic data. The heap just contains dynamically allocated memory, and the stack, which is fairly important for this talk, contains local variables, and it consists of these things called stack frames, which will be explained later on. So I've mentioned registers. However, there are a number of special purpose registers which are important for the execution of code. The most important one is probably the instruction pointer, which points at which instruction we're currently executing. This increments by one each time a line is run, and is altered by things like jump and return and call statements, instructions. There's the base and the stack pointer. The base pointer points at the bottom of the stack pointer points at the top of the stack. There's a flags register, which holds a number of important flags relevant to the code executing, such as the zero flag, which indicates that the result of the previous operation was zero. There's parity flag, which indicates whether the result of the last instruction was odd or even. There's the interrupt enable flag, which indicates whether interrupts can basically happen at this part of the execution. So, going back to the stack consists of stack frames, as I previously mentioned. These stack frames are created whenever a function is called. When you call a function, you push the instruction pointer and the base pointer onto the stack, and you set the base pointer to be equal to the stack pointer, which means that effectively you've created a new stack where the bottom of the current stack is the same as the top of the previous stack. And then anything which is then declared within that variable expands that kind of separate stack, the stack frame. Then when you return, after all variables have been used and you're back to just the saved base pointer and the return address, the return function will pop the instruction pointer back into the into the instruction pointer, and the base pointer back into the base pointer, so it returns to the previous state it was in. So if you're familiar with like variable scoping, where a variable only exists within a certain function, that's because once the function ends, the stack frame is destroyed, and so those variables are no longer accessible. Whereas variables declared in functions in the function that called the function you're currently in, they still do exist because that stack frame still exists under the stack frame you're currently in. This is relevant for like stuff later on in the talk. So I didn't know what to put here as an image, so um, so compiled code can be converted into assembly. There's a one-to-one correlation. How does this relate to stopping WannaCry? We could try to figure out how the encryption happens and see if we can undo it. We could look at how it spreads and try to prevent it. We could try to write an antivirus signature for it. Or we could hope that the malware authors put a convenient kill switch that we can trigger. So, what is reverse engineering? I suppose I have a slide here about never mind. I guess we're going straight into dynamic analysis then. And dynamic analysis is basically where you run the assembly code line by line, like you'd run any other code. It's kind of like a debugger in that way. And you're able to set breakpoints and see register values mid-execution. So if there's a bit of assembly which you don't really fully understand, you could set a breakpoint after it and see what happens to registers and kind of infer what went on through that. You can look at memory areas such as the stack and the heap, again, to try to figure out what code is doing without having to necessarily look at every single line, which is very useful. It speeds up the rate at which you can analyze binaries. However, you could accidentally encrypt your own files, which would be a bit of a pain. When working with malware like WannaCry in this example, there's also the option of static analysis. With static analysis, you can view functions and symbols, etc. And there's usually a decompiler. Some tools have decompilers, which will take the assembly and convert it back into a C-like language, which is easier to understand. I realize now I was meant to go on on a... Oh, this hasn't shown... Oh, there we go. Yeah, so I was going to demonstrate what certain lines of bits of C look like in assembly. So if anyone has any suggestions for lines of C to write to see what they compile to. No?
Hello world to start with.
Sorry?
Printf hello world to start with. That's something.
Printf hello world. I need to import the thingy. Printf is an stdio, isn't it? Oh, it's working. The issue is I can't see it from my laptop, which is a pain. But yeah, no, so the start of the main function is pushing parameters and stuff onto the stack, which is used for when you then later on have to return. So the base pointer and the instruction pointer are pushed on so that when you run the return statement, they're popped off, and the program can continue to where it was before. Then registers are used to hold parameters for functions, and once all the parameters are stored, you call a function. I can't see the call. Oh, there is a call there on line 11. Where it calls a function, the call will then set the instruction pointer to be the location of where printf is, and execution will continue there. The base pointer will be saved onto the stack, and there'll be a new stack frame within printf. Once printf finishes, the instruction pointer is popped off the stack again, and the execution continues into the main function we've written, where it then returns 0. Is there anything else you want to see in assembly?
Well, if we call that, calculate members, can you come up with that?
No, probably not. I mean, if you can give me an implementation of it, I could type it out for you, but...
I tell you what, let's do 2 and 2. Let's see what the arithmetic instructions look like.
Alright, this is awkward because I'm still on presenter view, so I'm looking at the PowerPoint. Wait, so you want me to declare an integer and then add...
Yeah, and add it, and we'll see the arithmetic functions I assume appear on the call.
Yeah, that did stuff. I can't actually.
I can't see very well. I can't see them.
Oh, I think this has probably been optimized out because it's not being used. So if we declare it as volatile, I think that should work. If you declare a variable as volatile, it basically tells the compiler that, like, even though it looks like this variable isn't being used, don't optimize it out because it might still be used somewhere. Did that change?
It's changed. Somehow I expected there'd be like synchro. Oh yeah, there's that.
Yeah, so it's like, yeah, it's saving it to a register and then adding to that register. But yeah, I suppose if there's nothing else, we can continue. This was meant to come after the stack frames bit, but then I just completely forgot. So yeah, so some tools have decompilers, which will turn the assembly back into something like something that's not quite C, but it's kind of like pseudo C, and it's easier to read and understand what's going on. However, the decompilation output isn't always perfect, which we'll see in the live demo, hopefully. And then you get cool control flow graphs, which show you how the execution flow goes, like where it branches off, where certain lines of assembly are run and stuff, which is quite useful, because then you don't have to like go through and find each jump and see which bits get skipped at certain points and things like that. And there's no risk of accidentally running malware on your own system, which is ideal. This is a really shit slide because I put no effort into it. So what other reasons is this useful for? Like, this is kind of going off of the whole, like, we're trying to reverse WannaCry storyline. Like, what other cool things can you do with software reverse engineering? Well, you can obviously work out what software is doing. That's kind of in the name. You can modify application behavior, which is known as patching, and you can find otherwise difficult to spot vulnerabilities. So to go into patching is where you directly modify the code without the source. So you go through and you change individual instructions, which is really useful because you can like skip authentication checks. You could change like a conditional jump to an unconditional jump and cause certain checks to be skipped entirely. You can pretty much change whatever the code does, which is very powerful. However, padding is a pain because the CPU requires things to be in certain length chunks, and when they're not, they have to be padded to be that length. However, if the padding is off, it will just not execute, and padding is a pain when you're patching. So I want to talk about return-oriented programming, but to understand return-oriented programming, we need to talk about buffer overflows first. So stack data often has a fixed size buffer. Like if you have a char array of size 5, that's a 5-byte buffer. If there's nothing controlling the data that goes in, the user can still input data that's larger than 5 bytes, and it will overwrite everything that comes after it on the stack. So if you, for example, had a char buffer and then an integer, you would be able to change the value of the integer by writing into the char buffer, depending on where it lies on the stack. So, yeah, data over the buffer size will overwrite other things on the stack, which is a buffer overflow. So, going on to return-oriented programming, this is super cool because, as I noted before, in the memory segmentation bit, everything other than the text segment is non-executable. That wasn't always the case. In the past, the stack used to be executable, and people would be able to write what's called shellcode on the stack and redirect execution to it, and like basically you have arbitrary code execution where where their code is on the stack, and they're just redirecting the instruction pointer to point to it. You can't do that anymore because the CPU will refuse to execute anything that's in a non-executable memory segment, which is everything other than the text segment in most cases. What return-oriented programming does is you pop a value from the stack into the instruction pointer using a buffer overflow, because remember, the instruction pointer is saved onto the stack. If you're able to overwrite the instruction pointer, you can point it to these things called gadgets, which are little bits of assembly within the text segment. Because remember, the standard library is a part of the text segment and contains loads of functions. You can find a couple lines of assembly which you want to run, which end with a return statement. And then you could have overwritten the next return value. So you string to another part of the text segment, which contains a couple lines of assembly you want to run that ends with a return. And by stringing these together, you effectively get arbitrary code execution, whilst the stack is still non-executable, because the code that's being executed is in the text segment, not on the stack. It's effectively arbitrary code execution. Right, so the bit where everything goes to shit, live demo. I hope this actually lets me view what's going on. Oh, yes, it does. Cool. Right, so I've already let Ghidra analyze this WannaCry binary. By the way, so obviously there's a kill switch in WannaCry, which was what ended it initially. However, then new versions were created without the kill switch. And the whole point of this demo was to try to find the kill switch. I spent about 4 hours analyzing a sample of WannaCry which didn't have the kill switch. I was up till 3 a.m. and I thought I'll run strings, which shows you all the strings within the binary. And I saw there was no kill switch there. And when I downloaded the right binary, I found it within 3 minutes. And by that point, I was done. So Ghidra has automatically pointed us to the entry function. That's the first function that's run, but it's not created by the programmer. This is default Windows code to kind of set up execution. And if you take a look at functions, normally you'll have a win main function, but because there's been some obfuscation, symbols have been removed, and therefore you can't identify the win main function through the symbols in the binary. However, you'll always be able to find the entry function, and the entry function will always lead to win main. This function over here should be win main. So we get okay, can you see all this, by the way? Is this readable? Reasonably. What about from the back? No. Okay, let me know when stuff is big enough. Is that better? Okay, so so what Ghidra has done is, we have the assembly over here, which we can go through, but we also have the decompiler output. And what we can do is, a lot of the data types in the function, because there's been a bit of obfuscation, Ghidra hasn't automatically been able to identify, so undefined 4 is just an undefined 4-byte data type of some sort. But we can kind of look at what's going on in the code and figure out what they are and redefine them, so we can improve the decompilation output that Ghidra has given us by looking at the code and the assembly and kind of deducing what things are. So, for example, puvar3 points to what's obviously a string. So we can find puvar3, which is an undefined 4-byte pointer. And if we right-click on it, we can retype the variable to be a character pointer. Then we can go through and do this with, all the other data types. So local 50 is copied into puvar4, which is a pointer to local 50, and then local 50 I remember it being somewhere here. It's... I mean, it's a 14-byte character array, so we can redefine local 50 to be char14, and then that cleans up a lot of the code because now that Ghidra knows what this is, rather than because all the other variables were basically it not recognizing that this was one large array rather than multiple variables because of obfuscation. Now that we've kind of identified that it's a 14-byte character array, it's automatically been able to clean the decompilation output and make it much more readable. So these like 5 lines is an example of where Ghidra fails to pick up on very like basic patterns. These are created by 2 lines of assembly, these 2 over here. And what this is basically, it is a repetitive move. If it lets me, like, this is movesd.rep, so it's a repetitive move, moving one thing to, moving the string to somewhere else. It's a string copy. So, if we change this to be a decimal value, it's kind of a bit more clear what's going on. We have ivar2, which is a part of this for loop where it's being constantly decremented, and then what we're doing is we're adding 4 to puvar3. Puvar3 is a pointer to a character, so we're advancing the character pointer by 4 bytes each loop. So we're moving along the character array, and we're copying puvar3 into puvar4. So we're effectively copying puvar3 into puvar4. This is just a string copy between those 2 variables. And so then what happens is Internet Open URL A will try to open a URL, which is obviously, the obvious URL is over here. And we can rename this to make it more clear what's going on. It's like we know this variable is a URL. And then we can call puvar3, the thing it's being copied into, URL copy. Which, yeah, makes it a lot more clear what's kind of going on with the for loop. We're then wait, sorry, I missed a bit I was meant to go over. So the function itself is undefined for. However, we already know that it's a WinMain function. So we can open up Firefox, and we can look up WinMain, and Windows documentation comes up. And going through Windows documentation, we can look at the function signature. We can look at the function signature and then copy that into Ghidra so that Ghidra understands what's being like copied, what the function is actually doing. It doesn't like the semicolon at the end. Yeah, so now Ghidra has a better idea of what parameters are being passed into it. And whenever you identify like a standard Windows function or a function that exists within documentation, you can go and copy the function signature into Ghidra to then improve the decompilation output. And then when we look in functions, we get the WinMain function, which is now identified because we gave it the function signature. All this data would normally be present, but it was removed due to the fact that there was some obfuscation with with WannaCry, and that's the case with most malware reverse engineering. So anyways, this strange like URL is the kill switch domain, and by registering it, it would prevent WannaCry from running because it checks that the kill switch domain isn't registered before continuing execution, and it will abort execution when the kill switch domain is registered. Originally, when Max registered the kill switch domain, it was to try to track infections of WannaCry. He didn't realize that it would kill WannaCry, but it did, which was kind of cool. Yeah, I suppose that's like a very ungraceful end to the live demo. And then, yeah, the end. If you have any questions.
So, any questions? Oh, there we go. Question.
Yeah.
So you look sometimes at the domain program, when you look into the gadget, you then want to build that the return point of that function too.
Yeah.
You do that by looking for functions that have, because obviously the function always needs to do that itself. Because so if you look for functions that have side effects, which also contain copies that you can exploit, you have a copy function, then the function you want to call, and run the copy function overwriting the next stack.
So what you do is you'll have, when you're overwriting the stack, you'll have a bunch of like return addresses, and so the first return address will be popped off into the instruction pointer, and that code will be executed and will hit another return. And if you have another return pointer which you have after that, that will then be popped into the stack, and then that code would be executed. And so it's like, rather than have a function itself which can facilitate adding another return pointer, you just have lots of return pointers in one kind of string. And yeah, each time a return statement is run, it will pop off the next return, and it will go off into another part of the code. And then eventually, if you know what the original instruction pointer was, which you can get through leaking values on the stack, you can copy that at the end and cause a function to continue normal execution after having gone off running these random bits of assembly where you've been returning to like random places. Are there any other questions?
Okay. Can you give another round of applause to Tom Wood and Tom? Thank you.